Okay, so now we left off on 6D. Let's get 6E. So we want to find the probability that the student is a STEM major given that he is a junior. All right, so I'm going to use a little bit of abbreviation here. We want to find the probability, and I'll just say STEM, given we have J for junior. And I'm using the whole word STEM because we have sophomore and senior, so I don't want to use S. All right, now let's remember our conditional probability formula is that we want the probability that they are STEM and a junior. So let me put my little intersection sign in here, over the probability of the second one in the notation, that they are a junior. All right, so the probability that they are a STEM and a junior. Well, if we look, here's all of our STEM going across here, and here's our juniors in this column. Those that are both a STEM major and a junior is 31. Now on the bottom, we want the probability that they are a junior. So if we add up all of these, and I think I had in the previous slide done that, but forgot to do it for this one. So we'll go ahead and add up this entire group of juniors. And that total of that entire column ends up being 577. And you can either put that in your calculator or reduce that fraction if it is in fact reducible. Let's go to number 7. For two events, A and B, the probability of A is 0.75, the probability of B is 0.46, and the probability of their intersection is 0.3. We want to find the probability of A union B. Now let's remember that we have a formula for union. That formula is the probability of A plus the probability of B minus the probability of their intersection. We have to subtract off that intersection. Otherwise, it gets counted twice when we add the probability of A and the probability of B. And this total should never be more than 1. If we don't subtract off the intersection, it will be. So we're going to have 0.75 plus 0.46 minus 0.3. And, oops, I forgot my point there. And I believe that is 0.91. All right, so let's go to B and find our conditional probability. Remember, our formula is the probability of A intersect B on top over the probability of B. All right, so the probability of A intersect B is 0.3, so let's put that on top. And the probability of B is 0.46. Now we do want to let our calculator change this thing into a much nicer decimal. And I'll take that out 3 decimal places, that's 0.652. All right, now let's do the opposite, or I should say the reverse, the probability of B given A. And that is again going to be the intersection on top. But our bottom will be the second one in the notation, the probability of A. So that's going to give us 0.3 divided by 0.75. And again, we can put that into our calculator, and that will give us 0.4. All right, now in D, we want to determine if A and B are independent and explain. Well, our explanation is really using the formula for independence. If A and B are independent, then the probability of A given B will be equal to the probability of A. Or we could have that the probability of B given A will be equal to the probability of B. We can use either one of them. All right, so that's our question for independence. Well, let's notice we did the probability of A given B. It was 0.652. And we did the probability of A. Well, we know the probability of A. It's 0.75. Those are not the same, so this is not independent. Now, if they were the same, of course, they would be 2 independent events. We can also say, instead of saying not independent, we can say dependent. All right. And our explanation is really our use of that formula. Mathematically or statistically speaking, that's enough of an explanation. We want to ask if that formula is true. It's not, so it's not independent. All right, so let's look at 8. Given the deck of cards in question 5, a single card is drawn at random. We want to find all of the probabilities listed here. So let's look back at question 5 and see what our deck of cards was. We had 20 cards with 5 cards from red, green, blue, and purple, and each of them numbered 1 through 5. All right, so red, green, blue, and purple. Since I have erased my sample space, let's just very quickly list that sample space again. So we have red cards numbered 1 through 5. And we have blue cards numbered 1 through 5. Green cards numbered 1 through 5. And purple cards labeled 1 through 5. So there's our sample space that we had from question 5. I may have listed them out of order from what I did before, but it's still the same sample space. So let's look at A. We want to find the probability that the card drawn is a 3 or a 5. All right, so let's notice how many 3s or 5s we have. 1, 2, 3, 4, 5, 6, 7, 8 3s or 5s. So that's 8 out of the total sample space of 20, which if we reduce, that's going to give us 2/5. We can change that into 0.4 if we want to change it to a decimal. All right, so let's take a look at B. We want to find the probability that the card drawn is a 3 or a 5, given that it is not a 1. Okay, so this is a conditional probability. We want to find the probability of 3 or 5, given not 1. All right, so let's remember our conditional probability formula. That's going to be that 3 or 5 intersected with 1, not 1 on top. All right, so divided by the probability of not 1. Okay, so I have a feeling we're going to get 1 here, but we'll see. Let's notice the probability of 3 or 5, all right, intersected with not 1. If we want to, and it may help us beforehand, if we list the event 3 or 5, that is going to be red 3, red 5, blue 3, blue 5, green 3, green 5, purple 3, purple 5. And then if we list the event not 1, well, that's everything that's not a 1. So red 2, 3, 4, and 5, and green 2, and I'm just going to shorthand here, 2 through 5, and blue 2 through 5, didn't mean to skip it, and then purple 2 through 5. Okay, and you may have noticed this without listing these out, that if we look at what they have in common, they have in common everything that is a 3 and a 5, which is everything in this first set. So let's notice everything in this first set. There are 8 of those out of 20. So our top probability is 8 out of 20. It's really, of course, what we found in part A. Now let's look at the probability of not 1. Well, I was wrong. It's not going to be 1. Okay, so let's see. We've got 4. There's actually 4 in there, 4 in there, and 4 in there. So 16 out of 20. And so the 20s will cancel out when we do our fraction operations. This will reduce to 1/2. All right, so now let's look at C. We want the probability that the card drawn is a 3 or a 5, given it is red or green. All right, now, again, let's look at the probability of a 3 or a 5, given red or green. Okay, so again, if we use our probability formula, we're going to have the probability of a 3 or a 5 intersected with the red or green possibility. And then that is going to be over the probability of red or green. Now again, to help us just a little bit, let's list red or green. So we'll have red 1s through red 5, and we'll have green 1 through green 5. So that's our event, red or green. So if we think about this event and what it has in common with 3 or 5, let's notice that it has in common R3 and R5 and green 3 and green 5. So that is 4 out of 20 for our top probability. And then our bottom probability, the probability of red or green, well, if we look at this, there are 5 cards that are red, 5 cards that are green, so that's 10 out of 20. Again, in our fractional operations, the 20s will cancel and we'll get 4 out of 10, or 2/5. All right, so let's take a look now at question 9. And I may not get through all of this because I am running low on time on the video, but we'll go as far as we can. So number 9, a random experiment gave rise to this contingency table. We want to find the probability of A, the probability of R, and the probability of A intersect R. All right, so let's start with the probability of A. I don't know why it's always giving me the extra letter. All right, so the probability of A, we want to add all the way across the A row. So that's 0.05 plus 0.21. That's going to give us 0.26. The probability of R, we want to add the R column. So that's 0.05 plus 0.37, which gives us 0.42. And then the probability of A intersect R, we want where A and R come together. So here's our A row, here's our R column. Let's notice they have in common the 0.05. All right, so part B, we want to know if A and R are independent. Now, this may help us to use the second definition of independence, which says that the probability of A times the probability of R will equal the probability of their intersection if they are independent. And this one's more useful in this instance just because that's the information that we have. So we're going to have 0.26 times 0.42. The question is that equal to 0.05? So let's do that computation on the left and see if these two are equal. So the left computation, and oops, I'm going off the screen, let me move up, gives me 0.1092. That's definitely not equal to 0.05. The answer is it's not independent. Or if we want to, we can say dependent. And I'll stop there and go to another video because I'm about to run out of time on this one.